disclaimers. The first one, it's not about the twisted bilayer graphene, and second, the Darwin term and p to the power 4 term were excluded. Okay, so let me start. Oh, something is not working. Yeah, I didn't put it on. Okay, so I think after these 2.5 heavy days, I don't need to tell too much about the physics of spin in graphene or in other low-dimensional materials. But basically what we learn is that spin is affected by almost everything. So contacts play a role, substrate, atoms, measurement devices, and etc., etc. And there is a plenty of phenomena which is related with the spin or can affect the spin dynamics. And I will also not go into deep details of that. Just what I wanted to add here is the superconductivity and tell you something about that. So basically, those things you can find in those two nice review papers. I highlighted by yellow color all the people who are here, and you see that the organizers did a good job because you see that it's almost yellow. And let's say for family-like reasons, I also would like to introduce the Igor and Alex paper, because it's about the proximity materials and superconductivity, which I will talk would be of the proximity nature. And since we are many of us are here, I would say we can also proximitize. So folks, let's proximitize. Okay, so now let me come to the motivation. So true motivation which I have is coming from the Spintronics. And those who are doing a graphene Spintronics, they know that there is this almost Hamlet-like question. What is causing the spin relaxation? Is it the magnetic moment, or is it the spin-orbit coupling? Spin-orbit coupling which is global or local or random or something like that. That's the first sort of question you can ask yourself. And the second one is whether the mechanism which is behind this normal scattering or it's something more exotic, and say resonance scattering. And I will try to convince you that doing the experiment in the superconducting phase of graphene can help to unveil or can answer partly those questions. Okay, so I think after the Roland talk and Ahmed talk, I think I don't need to tell too much that we know that the impurities are bringing the magnetic moments to the graphene. So based on the DFT calculations either done by Oleg or Martin, we know that light atoms like hydrogen, vacancy, methyl group, if they are placed on the top of the graphene, they will induce the magnetic moments. So they are there. There are also strong experimental evidences for that, and Roland was explaining us basically results of the common work with Yarrow about some fluctuating time-dependent random field, but there are also another measurements like the universal conductance fluctuations or the Wig localization or the mentioned Madrid experiment in Ivan groups, basically pointing out that there are magnetic moments. And the last things, I want to say that we like the resonances. I was just piling up a few papers which are dealing with the resonances, and also most of the papers I took are from the people which are in the audience, but there are also some experimental, let's say, evidences that resonances are here. So here I want to point to the paper of Zeldov group when they are able to explain some transfer, assuming that there are some resonance states in the graphene, or as Roland was explaining us, we did some nice work about the transport spectroscopy and somehow unveiling that there are some resonance states. So here I want to make one comment, because every one of us, we like the resonances, and I think we studied a lot of them, and maybe you are using our Hamiltonian, so I want to make one warning. And the warning is that if you are working with the resonances, that we are having some enhancement of the density of states and also the transport in this region. But as the concentration of resonances is growing, what happens is that there appears a mobility edge, and basically what could happen is that those states are localized states at the end. So this is the function how the mobility gap changes as a function of the concentration, and it could really very often happen that if you are crossing some characteristic concentration which is dictated by the graphene bandwidth and the resonance energy, basically we will see that those states are not extended states, but they are localized states. So basically those guys who are doing transport based on the Green's function, I just want to tell you that from time to time it's necessary to check whether the Joffe-Regel mode criterion is satisfied. Since calculation can be run, you will get the result. But I would say that if the transpose is mediated via the localized states, I think it's breaking the coherence. The second comment, I think that was yesterday, some comment regarding the Stefan paper. So I think in 2017, we with Susanne and Yarrow, we were studying all possible atoms, and I think we proposed the most general Hamiltonian for that hollow position impurities. So basically anyone who is using that Hamiltonian has intervally scattering there. And this is just the comment to Iris paper when they are having the same conclusion, but somehow collegially they were not referring to us as well. Okay, so let me return to this spin relaxation and the question I posed. And now let me tell where is the answer. And the answer is that S-wave superconductivity is responsible for two things. The first one is that if you are having a magnetic impurity in the S-wave superconductor, then spectroscopically such magnetic impurity will also lead to the localization of the bound states. This is the fact number one. And the second one is that if you are computing the spin relaxation rate in the superconducting phase, and you compare it with the spin relaxation rate in the normal phase, what appear up is some combination of the coherence factor. And this combination can be constructive, which would be this plus sign, or can be the destructive, and this would be the minus sign. And what discriminates which sign is here is the parity, or basically time reversal symmetry of the interaction. So the plus sign you will get for the spin relaxation for the impurities which are odd with respect to the time reversal symmetry, which would be the magnetic impurities. So that you would expect that there will be the faster spin relaxation because I am making some coherent superposition of some things, which in average will put some factor which is larger than 1. However, the minus sign appear for the perturbation which are even, which are odd, which are even with respect to time reversal symmetry, which would be the case of the spin orbit coupling. So basically, what does it mean is that if the spin relaxation is dominated by spin orbit coupling, you should see that in the superconducting phase it will go down. So it will be the spin relaxation time will be longer. Okay, so why this is so? So let's say the answer can be mathematical. So basically, going to the superconducting phase, you are not working with electron and holes, but you are working with Bogolyubov quasi-particles, and then you are doing some mathematics and you will get it. So basically, at the point when you substitute those guys here and do some mathematics, assuming parity plus or minus, you will get that. But this is, let's say, too formal. And let me give you some childish arguments. So people like childish formalism, I like the childish formalism. And I want to try to explain you what is the physical ground for those two differences. So let me start with the simplest case that I have a parabolic band structure, and I'm fixing somewhere my chemical potential. So in that case, what I'm having in the game are the electron and hole excitations, which are living outside or inside of the Fermi sea. And if I have in the game electron-phonon coupling, then the situation around the Fermi energy will change, and what would happen is that I will get the quasi-particles. So the quasi-particles are having some gap, delta 0, and you are seeing the dispersion relations for them. And now comes the main thing is, let's compare the group velocities of those particles. So the group velocity of normal particles is just the derivative of the energy. But if you are taking the group velocity of the quasi-particles, you should differentiate with respect to the momentum the quasi-particle dispersion relation. And if you do a simple math, you will get that there is this prefactor inside. And you are seeing that around the Fermi energy, basically you are seeing that this is almost, derivative is almost 0. So what we are seeing is that quasi-particles in the superconducting phase, they are much, much slower than the normal particles in the normal phase. And these have consequences for the spin-orbit coupling, since we know that the spin-orbit coupling is effectively momentum multiplied with a spin time gradient of some field. And if you are seeing that the velocity is much, much smaller, then basically this is the physical, say, one of the physical mechanism, one there is a minus, because quasi-particles are slow and they are relaxing longer. Okay, so based on that, we should expect that the spin relaxation in the superconducting phase, if it is done due to the spin-orbit coupling, should be suppressed. And this is not thing which I discovered. This is the old known things from the Yafet and also many others. So this is the formulas Yafet had in that paper. And basically this is the difference of those coherences factors which I was describing. And basically what you are seeing here is the ratio between the spin relaxation rate in the superconducting phase to the spin relaxation rate in the normal phase as a function of the reduced temperature. And basically you are seeing that according to this Yafet formula, this should go to the 0. And there were already some experiments done in the ultra-thin aluminium, and I hope that maybe some people can also repeat them in the superconducting graphene. And basically they are really reporting that there is a or basically 6 orders of magnitudes difference in the spin relaxation in the superconducting aluminum compared to the spin relaxation in the normal case. Okay, so let me give you also the reason why in the case of the magnetic moments the spin relaxation should go up. And in that case, again, we are having our picture of the quasi-particles, and this is the corresponding density of state. And basically, who is contributing in the transport are the quasi-particles, which are only thermally excited, so it means it is those guys. And those guys, they are having almost the same effective mass as the normal carriers, but they are having much, much lower effective charge, because effective charge is anything between plus or minus electron, because this is the superposition of the electrons and holes. So as a consequence of that, the basic mechanism is like that. So normally you would say that I am having incoming electron, which has some kinetic energy. I am having some impurity state, which is occupied by opposite electron. So now the kinetic energy is spent for the charging energy. And now this electron is leaving the story, and basically we effectively get a spin flip. And as I was telling you, that the charges are much, effective charges are here much, much lower. So we would expect that this charging energy in the superconducting case would be much smaller. But you should also remember that also kinetic energy is smaller, because I was just telling you that the velocities are changing. So what would matter is the ratio between the kinetic energy to the potential energy. And if you are taking the kinetic energy around the Fermi level, it goes linearly with the velocity, and the charging energy is going as a quadratic with the charge. So if you are plugging the characteristics numbers, you are getting that, okay, in that case, this ratio should favor the spin relaxation. And this is basically one mechanism behind that there is the enhancement of the spin relaxation. And this is also a known phenomenon. And this phenomenon, or this experimental fact, is going under the name as the Hebel-Slichter effect. So this is the Chuck Hebel, and this is the Charles Slichter. And basically, again, we are having a characteristic picture in that case, that this is the spin relaxation rate in superconducting in normal phase as a function of reduced temperature, and this is exactly the effect you are seeing. So if there is the onset of the superconductivity, spin relaxation go up, and then basically, because you are with lower and lower temperature, you are having less and less quasi-particles in the game, it's going to zero. There is a question by Stefan.
Sorry for interrupting, but just to keep going, you speak about spin relaxation time and the superconducting state. So how do you define the spin when you say spin relaxation time of a Cooper pair?
It's about the quasi-particles.
So how can you define the spin state
of quasi-particles? This is the excitations of the Cooper pairs. So you have a thermal excitations, and some portion of the Cooper pairs is thermally excited to occupy the quasi-particles, and the quasi-particles, they are having well-defined spin. Yeah, so yeah, that's a good point that I didn't really emphasize, that is the spin relaxation of quasi-particles. Okay, so if I would be experimentalist, which I am unfortunately not, then basically what I need to look is how the spin relaxation rate behaves when I'm lowering the temperature. And if I would see decrease, I am saying, hurrah, it's a spin orbit coupling. If it is increase, I could say, yes, it's a magnetic moment. Okay, so there is a question.
Okay, so I'm just a bit confused about that relaxation time being associated with the quasi-particles, because the Hebel-Slichter effect that you're showing there is a statement about the relaxation time of nuclear spins, and through the excitations that they can generate in the quasi-particles, completely independent of what the spin relaxation of the quasi-particles is itself.
I think it's the spin relaxation of the nuclear spins, which is mediated by the conduction electron, which are in the superconducting phase, which you can say, like, conversely, the spin should go somewhere, so also electrons will relax.
Right, but it's not at all limited by what the spin relaxation of the quasi-particles is. It's just a rate of dumping spin into the quasi-particle system. So it's a Fermi's golden rule calculation.
Yeah,
so
exactly.
So it doesn't depend at all on what the spin relaxation of the quasi-particles themselves is. And so that's why I'm a bit confused by how this is connected.
Okay, so maybe from the calculation it will be clearer, or we can then maybe discuss later. So the model, so I am considering the superconducting graphene, and basically we know that the graphene is not intrinsically superconducting. So basically you can imagine it like that. The quantity which tells you that something becomes a superconducting is that you need some good combination of the density of states and the electron-phonon coupling, and et cetera, et cetera. And basically, the reason for that is that if we want to make a graphene superconducting intrinsically, then we would like to have this quantity to be larger as possible, which we can do if we will maximize the numerator and minimize the denominator. So one thing for that would be that we are talking about the density of states of the electron, and the p electrons in graphene, basically they are vanishing around the zero. So one way would be let's try to have a high doping. So this would really definitely help, because we will get these things larger. But on the other side, we are needing a coupling to the phonons. And if you are looking for the pristine graphene phonon dispersion relation, you need a coupling to the phonons which are having a proper quasi-momentum. And there are 3 acoustic branches, but unfortunately that one, which has the lowest omega, is not coupling from the symmetry reason to the p electron. Only those phonons which are higher energy are coupling to that. And the argument is very easy, because if you are computing these displacement matrix elements, basically you are seeing from the symmetry that on one upper side of the graphene, this force is negative. However, on the downside of the graphene, it's positive, and you are having overlap of plus and minus and minus. So basically, no calculation is needed, just the counting the signs, and you see that for pz electrons, this is useless. So you really need a coupling to the not out of plane phonons, but to the in plane phonons, and those in plane phonons that you are seeing, they are higher in energy. And basically, all theoretical strategies which were done are basically how to get this number large. So basically, people are proposing, okay, go to the higher doping, and in the higher doping, you will also discover that there are also other possibilities possible. Other idea is, let's put graphene on top of something which is superconducting already, and then by proximity effect, we can get the superconductivity or graphene. Or another possibility was to use the alkali intercalation, that you are intercalating here, let's say, some alkali atoms, and this on one side breaks the symmetry, so this coupling start to be allowed, and also enhances the density of states around the charge neutrality point. So basically, this is all the ways how you can do it. And the other possibility is the twisted bilayer graphene, which I am not discussing. Okay, there are already some experiments. So I think the first one was done in the Morpurgo group in 2016. So basically, they take 2 superconducting electrodes. The graphene was beneath, and they were able to induce the lateral superconductivity in this system. Or you can put the graphene on top of something superconducting, which was shown on those papers, or all these intercalations. Basically, some taking home numbers is that the superconducting temperature is something from 0.1 to roughly 5 Kelvin. I think this is not updated numbers. The superconducting gap is ranging in this energy range, and both S-wave and P-wave superconductivity was demonstrated in graphene. Okay, now comes the model calculation. I still have 12 minutes, so I think I will do it. So basically, our model is like that. So we are having a superconducting graphene, and this superconducting graphene is described by the Hamiltonian H0. So it is the standard nearest neighbor coupling. Then I am assuming that my graphene is in contact with some reservoir which defines the chemical potential. And I am assuming that the experimentalists would be able to change it by the doping. And then I am assuming the standard S-wave superconducting pairing described by this term. And I'm considering that in principle gap can be temperature dependent, because let's say superconductivity is induced by some host superconductor. So I'm considering the standard tangents hyperbolicus dependence of that. And then I am assuming that I am having some adatom which is hybridizing with the graphene, and this adatom around of it can basically enhance the spin orbit coupling locally, or it can bring a magnetic moment. And I am independently investigating spin relaxation in this scenario and spin relaxation in this scenario, because they are on different energy scales. So basically, I am believing that the rates could be just Matheson rule combined. Okay, typical numbers of micro electron volts is for spin orbit coupling, and about 400 micro electron volts for the magnetic moment. Okay, so let me show you those resonant features. So this is the picture which we already saw. This is the density of states in the presence of resonant impurities. And now I am assuming that I am plugging my Fermi energy here. And now I am turning the system to be the superconducting. And now the question is how the quasi-particle spectrum will look like, and the quasi-particle spectrum will look like that. Then you can change the Fermi energy. And you are seeing that the traces of the resonance is also seen in the quasi-particle spectrum. So you are seeing that the quasi-particles in principle see that there was a resonance on the normal host. And taking that and adding the spin orbit coupling, I was calculating the spin relaxation rate. And this is the spin relaxation rate as a function of the chemical potential. So I'm assuming that this chemical potential I am able to change. And this is the figure. So rate as a function of chemical potential. And you are seeing that there is the enhancement of the spin relaxation, and this enhancement is due to this resonance process which I was explaining before. Electron or quasi-electron is coming, or in that case electron, because we are above the critical temperature. Electron is coming, it is orbitally locked around the impurity. Impurity has a long or strong spin-orbit coupling, then electron flips and leaves. And now let's see what happens if we are lowering the temperature. So now I'm going to the superconducting phase, and I'm slowly lowering the temperature, so the gap is larger and larger. And what you are seeing is what we already know from the Yaphet. So the spin relaxation as a function of temperature, if I'm cooling and cooling and cooling, is going down. So this is the, let's say, boring result, or something which was anticipated by Yaphet in 1983. Okay, and here there is just the comparison that the same, what I was telling you for the hydrogen is also working for the fluorine atom, and I also tried some other ones. So this seems to be a general trend that the spin relaxation should go down. Okay, now let me go and discuss the case with the magnetic moment. So in that case, I'm assuming that I have an odd atom, and this odd atom is having some local magnetic moment sitting on top of it. So this is again our density of states due to this resonance. Because of the exchange interaction promoted by this magnetic moment, this resonance is splitting. And now again, the same picture. I am above the superconducting temperature. So this is the standard in that case, it is the relaxation of electrons and holes as a function of Fermi level. And we are seeing those two peaks in the relaxation as a basically some artifact or as a consequence of this split resonance. And now let's see what happens if we are again going to the superconducting phase. So in that case, I am again lowering the temperature, and what you are seeing is a strange behavior. Outside of the resonance, we are seeing that the spin relaxation is going up, but inside of the resonance, it's going down. Yeah, and this is something which was not anticipated from simple Fermi-Golden rule. So basically, I was just putting my chemical potential to the resonance, and I was just plotting this Hebel-Slichter ratio as a function of the critical temperature. And you are saying that in the resonance, this is going down very much. So, and you should need to look for this left scale, which is a logarithmic one. However, if you are outside of the resonance and you are start to lower the temperature, you are seeing that this is the standard Hebel-Slichter scenario. So basically, relaxation is going up to some point, and then it's decreasing to the zero. And so basically, this part is clear outside of the resonance, but failed to explain what happens in the resonance. And for that, we were, okay, so again here, this is the picture for the hydrogen. This is the picture for the fluorine. Okay, the resonance region in the case of the hydrogen is around the Dirac point. In the case of the fluorine, it is outside of the Dirac point. And basically, again, we are having the consistent scenario in both cases, going down in the resonance and going outside of the resonance. And then we wanted to explain it. And for the explanation, we were looking for the position of the Yu-Shiba-Rusinov states. So basically, in 60s, three gentlemen independently discovered something what is today called as a Yu-Shiba-Rusinov states. And the idea was very simple. So assume I have a metal which has a parabolic band structure, and we are having some fixed doping on the chemical potential mu. And now assume that you are having a magnetic impurities there. And so what those guys showed is that if you are now turning the system to be superconducting, what happens is that you are getting this quasi-particle density of states, but inside of the superconducting gap, you are getting some localized states. And okay, in the Shiba paper, one can find the formula when the density of states enters and the strength of the magnetic field, etc. And basically, it's related with some singularities. And such things we already measured. So this is the measurement of the Yu-Shiba-Rusinov states on top of the niobium diselenite in the superconducting phase. And really, those people in France, they were able to measure approaching it from the different sides or changing the bias. They were able to see spectral features of those guys. So basically, this is the things I was telling you. So if there are magnetic impurities and you would be able to do some STS measurement, you should see some spectral features of those. Okay, and this is the case how it looks like in the case of the hydrogenated graphene. So this is the position of the Yu-Shiba-Rusinov states as a function of the Fermi energy for the hydrogenated graphene. And basically what you are seeing is in this resonant window, the position of the Yu-Shiba-Rusinov states is deeply inside the superconducting gap. However, outside of the resonance, it is quite away. And this comes really as from the calculation from the T matrix. So basically, you see that there is such a regime of the decoupling. And if you are in such a regime, basically your magnetic moment is decoupled from the quasi-particles. And basically what happens is that there is some virtual tunneling. And this virtual tunneling basically suppresses those things by the difference in the position of the Yu-Shiba-Rusinov states and the conduction or conduction quasi-particles. So basically more and more things which you are getting here, those guys are large, the difference is larger, and basically this is the reason why the spin relaxation is going down. So basically here I am with my conclusion already. So I was trying to convince you as a theorist that the superconducting graphene is offering, at least for theorists, some new platform for computation, something. And I was showing you some results for the spin relaxation in the presence of local spin-orbit coupling. So it is, in a sense, a Elliott-Yaffe mechanism, and also for the magnetic moment. And we see that in that case, the spin relaxation went down. However, in this case, outside of the resonances, it went out. And basically, the things are published on the archive. I am still waiting for some numerical data, which I want to put along to the theory, which is that, and resubmit it. And as an outlook, we want to look more carefully for some Diakonov-Perel spin relaxation mechanism in graphene. Then also the spin relaxation, if we will have a triplet superconductor, or the superconducting gap will be non-isotropic, because here the superconducting gap was isotropic. And this is also a nice thing. Or there are these Ising superconductors, and there is a very nice spin valley coupling and superconductivity. So this is also the one area I want to go and explore something. Thank you for your attention.
We do have some time for a few questions. Anyone?
So some dopants, if you dope graphene with some addatoms, some show resonances, some of them don't. And this Yu-Shiba-Rusinov states, did they mention something about resonance magnetic impurities or not? So
No,